All right, guys, now that you know what a dot product is, or now that you know what a vector is with the coordinate style, let's talk dot products, because fortunately they're not actually that hard. There's lots of stuff you can do with them too. So we got two vectors. We got u, which has x component u1 and y component u2. And we've got vector v, which has an x component v1 and a y component v2. If we dot the two together, we're just dotting these two things, and all dotting two vectors is mathematically, like just as a process, is you take the x components and you multiply them together, and you take the y components and you multiply them together, and then you add up those together. If we had a 3D vector, it would be much the same. We'd have the two x components multiplied together plus the two y components multiplied together plus the two z components multiplied together. And you can actually, if we're not talking about three-dimensional space, if we're talking about properties, you could keep going. You could have a 10-dimensional vector dotted with a 10-dimensional vector. They do have to be the same length, but it's a pretty easy process. Your first components multiplied together plus your second components multiplied together plus your third components multiplied together plus your fourth, and so on, however long your vector is. So here's some examples which I'll get you to do. Here's solutions if you're interested. If you dot something with x component of 4 and a y component of -1 with something with an x component of 8 and a y component of 3, the 4 and the 8 go together. 4 times 8, 32. And the -1 and the 3 go together. -1 times 3, you got -3 plus 32, we get 29. Anyway, I will assume you have the gist. You can follow the math here and pause it if you're having trouble, but I suspect you can handle it. Let's go over some of the properties of the dot product. It's something called commutative, which means order doesn't matter, which kind of makes sense if you think about what we're doing. We're multiplying together the first two components and then adding the second components multiplied together and then adding the third components multiplied together. So order doesn't really matter because both multiplication is commutative, and the addition, usually we consider it to be in the same order, not that it would matter. Anyway, so I showed it right here as u1 v1 plus u2 v2, which would be if you had your u1 v1 dotted with, u1 u2 dotted with v1 v2, you'd end up with this. If you reversed it and had v1 v2 dotted with, whoever wrote this screwed things up. This is v dot u. That should be a u. v dot u. So v1 u1 plus v2 u2. There was one other that was screwed up. This one was screwed up too. I'll fix that. U. Silly universities. Anyway, the second property is kind of comes right from Pythagoras. If you dot a vector with itself, you get the length of that vector squared, which kind of makes sense because if you dot it, you got u1 times u1. If you dot it with itself, you'd have u1 times u1, which is u1 squared, x component squared, plus u2 times u2, which would be the y component squared, and that equals the length of it squared. So if you imagined it as a right angle triangle, which is fully reasonable given that this is your x component squared and this is your y component squared, you're going to get the length of this thing squared, right? So yeah, just from Pythagoras, it's very naturally evolves. Think about it for a sec. Remember, u1 is just your x component, u2 is just your y component. Put it into a triangle, Pythagoras, you're good. The zero vector multiplied by any vector is also zero. And again, order doesn't matter. which kind of makes sense. Your 0 vector, you have a 0x component and a 0y component. Dot those together. You have 0 times u1 plus 0 times u2. Obviously 0. 0 times anything is just 0. So we have a couple of zeros added up. This one is a bit of a fun one. This is associative principle, I believe. So u dot v plus w equals u dot v plus u dot w. And so I proved it here. So you'd have, remember if you add vectors, thinking back to this guy, it's super easy. You just add up the components. So you got A's x component plus B's x component equals C's x component. And C's y component is just A's y component plus B's y component. So adding them is super simple. The component of this component of v plus w would be v1 plus w1, and the y component would be v2 plus w2. And so if we put that to the natural conclusion, if we dot it, we'd end up with u1 times v1 plus w1 plus u2 times v2 plus w2. We're just dotting these x component times x component, y component times y component. And then I fed the chickens and I regrouped stuff. So we have u1 v1 plus u1 w1 plus u2 v2 plus u2 w2. But I got all the things with v's together over here and all the things with w's over here, and I put brackets around it just so you could see that, hey, wait a second, this is just u dot v right here, and this is just u dot w there. So that's my little proof for that guy. And then I've got sort of a similar guy proof for this guy right here. How if you multiply it by a scalar, if you multiply it by a constant, keep in mind if you multiply something by a constant, like let's say I multiplied 4,2 by 2, I just multiply the x component by 2 and the y component by 2, so it would become 8,4. So yeah, multiplying by a constant, you just multiply every component by that same value. So in this case, if I was saying that cu dot v would equal cu1, which would be the x component of cu, times v1 plus cu2 times v2, because cu would be the y component of cu. And then we got exactly the same here, except we moved the c over. Now it's multiplying v1 and v2 instead of u1 and u2. But as you can see, after the dot product, given that order doesn't matter with multiplication, it is commutative. It's exactly the same thing. And then if we were to multiply the result of u dot v by c, notice it's exactly the same. If we were to feed the chickens, we could end up with either one of these guys. So yeah, all of these things are true. Hopefully it makes sense why. Let's keep on trucking. And then the next thing, it says find the length using dot product. Length squared is just a vector dotted with itself for reasons explained right here. If you dot a vector with itself, you get the length of the vector squared, because Pythagoras. And so if we want to find the length of this guy, we just dot it with itself. -2 times -2 is 4. 4 times 4 is 16, and we got to take the square root to find the actual length, and we end up with root 20 or 2 root 5. I'll leave the rest for the next video.